Thank you. As organizer of this symposium, I wasn't supposed to give a talk, but one of our speakers could not come to Japan, and this talk was prepared last night. It is heavily DFT with a little bit data analysis at the end of the talk. I would like to show you our efforts in theoretical designs of complex oxides for solid oxide fuel cells, on which our laboratory worked for quite a time. So my laboratory at Aleksandar is focusing on theoretical research, DFT mainly, but also different theoretical methods and different theoretical techniques, like machine learning a little bit, also molecular dynamics. And we work on all kinds of materials, starting from metals and for application in metallurgy, nanoparticles, catalysis, carbon nanomaterials, MOF, and different catalytic surfaces. We are reaching to complex oxides, mainly perovskite oxides, for application in solid oxide fuel cells. So today I would like to show you several different topics. First, oxygen dissociation on strontium oxide terminated perovskite surfaces, on lanthanum oxide terminated perovskite surfaces. Talk about the difference between those two. Some small molecules interactions with perovskite surfaces, cation mobility and the importance in cation mobility. Oxygen dissociation on lanthanum and praseodymium terminated Wilson Popper surfaces, the difference between lanthanum and praseodymium. Oxide mobility in several different oxides used as electrolytes in solid oxide fuel cells. And then some novel statistical approaches we apply in understanding or designing oxide diffusion within perovskite materials. So that would be a very simple, oversimplified model of a solid oxide fuel cell based on perovskites. And I don't know why this appeared here. And in that model, we would have the perovskite structure. We would have fuel electrode. We would have air electrode. On the fuel electrode, we'll have hydrogen interacting with lattice oxygen, forming water. Air electrode, oxygen dissociation reaction. Vacancy will modulate mobility, and we'll have vacancy flux towards the air electrode and oxide flux towards the fuel electrode. One of the important bottlenecks would be the oxygen reduction reaction, and from the very beginning, we were focused on understanding the oxygen reduction reaction in those materials. We use DFT calculations, utilize both plane waves and linear combination of atomic orbitals, both with fast software, quantum ATK, and we are calculating exclusively the entire diffusion coefficient based on this Arrhenius-like equation, where we have the activation barrier in the exponential factor. In the pre-exponential factor, we will have the vibrational term, translational term, rotational term, which more or less would account for the entropy. Now we focus on perovskite materials with AO termination. For those of you who are not coming from solid-state ionics, this is the Boring surface of perovskite materials. It is considered as a Boring surface because usually those A cations are large cations within the perovskite structure, which are catalytically inert. Now, all theoretical chemists were expecting the BO2 surface to be catalytically active within solid oxide fuel cell until several experimental teams, mainly led by Aleksandar experimentalists, have shown that in all perovskites exposed even for a short time to higher temperature and also moderately high oxygen partial pressure, AO terminated surface will be stabilized. And of course, for theoretical chemists, was really a big surprise when we are lacking those big cations, which are really catalytically active. What is catalyzing the oxygen dissociation reaction there? So the first thing we looked at was oxygen vacancy mobility close to the surface, and the oxygen vacancy mobility close to the surface demonstrated that indeed oxygen vacancy would preferably be stabilized within the surface layer. The second important thing we looked at is oxygen vacancy mobility or oxide ion mobility to a vacant site above the surface. Now, in the field of solid-state ionics, you will have many people telling you that spherical hydrons is a very important thing, and the more space you have around the lattice, the easier it will be for ions to move around. This is really counterintuitive for chemists. If that would be true, a jump of an oxide over the surface would be preferable. There is no any spherical hydrons, but actually it would come at a much higher activation barrier. So apparently, those connections between oxide ions and P-side cations and also A-side cations are what is utilizing the oxygen mobility within those materials. So spherical hindrance would be much less important compared to interactions between oxygen and cations in the lattice. Then we have demonstrated that those vacancies on the surface, indeed on those boring strontium oxide terminated surfaces, would be the active site, the catalytically active site for oxygen dissociation reaction. Now, dissociating oxygen molecules requires electron density. That's the only way you can split to oxygen. So the surface has to provide electron density to the oxygen molecule. One electron being provided to an antibonding pi orbital will make the superoxo species, and 2 electrons would make the peroxo species. So we were very much challenged if indeed that model, that catalytic model for the oxygen dissociation or oxygen reduction reaction on the surface is sound and more or less is it indeed the oxide vacancy acting as an active catalytic site, or it would be the entire surface acting as a catalytic site, and the work function of the entire surface will be important. Now, in chemistry, we really look at active sites, so we really wanted to show to the oxide community that yes, those active sites are the key, and we have to identify them. So we looked at strontium titanate, iron within the material, and then we look at surfaces with and without vacancies. So if the surface has no vacancy, indeed iron doping would bring more electron density within the material, decrease the work function. However, that electron density is not equally distributed to the slab. It is still localized close to the iron atoms. Once we have a vacancy on the surface, however, we'll see increased electron density between the top layer and the subsurface layer. And looking at the electron density distribution within the vacancy, we see that vacancy is not just a void, not just an empty site. Electron density, and that would be what will catalyze the reaction. Then we implemented the non-equilibrium Green's function method, which is usually used in the field of nanoelectronics and molecular electronics in order to demonstrate it. And we reproduced what we call computational STM experiment. So we would have an oxide electrode and a gold electrode, and we would have a 1 nanometer scattering region between them, oxide and gold. And we will calculate the probability of electron transport from the oxide electrode to the gold electrode. The gold electrode will be positive, oxide electrode will be negative. So if we have this would be the pristine oxide surface with a vacancy in the top layer, oxide surface with a vacancy in the subsurface layer. So in the case of the pristine surface, we will have very low current outside of the oxide to the gold tip, and it will require very high bias. In the case of vacancy in the subsurface layer, we will have an IV curve, which is resembling a pretty similar pattern. We need very high bias and we will get very low current. But once the oxide vacancy is within the top surface, we will have a lot of electron density streaming out of the surface and reaching to the gold tip. Or more or less, oxide vacancies on those electrodes are the gates, the doors for electrons to leave the material, and hence those are the gates and doors for catalytic activity towards oxygen reduction reaction. So we were immediately challenged when we had these results from our experimental collaborators who said, well, that's very interesting, it's a nice theory. However, how about lanthanum nickelate? That's a rhodesium copper oxide. And as a rhodesium copper oxide, lanthanum nickelate is known to have excess of oxygen, more than stoichiometrically needed. So all the vacancies within the material are being usually annihilated. Or we would not have any vacancy composition, yet the material is showing experimentally pretty good exchange with the oxygen from the atmosphere. Well, we wanted to see what is making it special. Lanthanum was expected to be a quite boring element, again, similar to strontium. We performed the calculations and we've seen that indeed lanthanum nickelate is catalyzing the oxygen dissociation reaction. Now that came as a surprise. We looked where the electron density is coming from, and we saw that this electron density for the oxygen splitting reaction or oxygen reduction reaction is coming from no other place but lanthanum itself. Now, in the field of solid state ionics, lanthanum is expected in those materials to be in charge of +3. So hence, lanthanum has no free electrons, no available electrons and electron density to donate to oxygen, and it shouldn't be catalytically active. Yet, our calculations were showing that yes, there is residual electron density at lanthanum, and this residual electron density was indeed necessary for was indeed the electron density catalyzing the reaction. So at that time, I had a very capable postdoc. I asked him, go back, take all the computational methods available. That's actually not everything. It's only in the paper. We actually got all the computational techniques we have. And I asked him to calculate me the charge of lanthanum in different oxide materials and calculate me the charge of strontium in different oxide materials. Now, to our surprise, lanthanum came always with a charge of close to +2, far away from +3, which would be the expected charge in those ionic materials. So strontium was coming properly close to +2, just like predicted. So strontium was boring, but lanthanum not at all. We looked where this electron density of lanthanum was, and the remaining electron density, and it was actually located at the d electrons. And certainly, as the theory of rheumicity was created, it started with a theory for bonding between the first and seventh group of the elements. And yes, indeed, they are very ionic. However, then it was carried over to the entire periodic system. And the elements within, between the seventh and the first group of the elements, they actually do not really obey those complete charge transfer between cations and anions. You have a lot of residual electron density, or ionizing d orbitals is very different from the ionizing s orbitals. So our simulations show that there is a residual electron density at lanthanum. It's making partial covalent bonds. Here I want to stress on partial, not real covalent bonds. Partial covalent bonds with oxygen in the lattice. And when those partial covalent bonds are cleaved on the surface, the residual electron density remains dangling. Orbitals of lanthanum remain with electron density population. And similar to a very poor transition method, lanthanum actually nicely catalyzes a high temperature oxygen reduction reaction. Experimentalists were not very happy with it. They said, prove it. We theoreticians, we don't like really to prove things experimentally. But at that time, the postdoc working with me was very keen to show that this works. So we performed experimental results with the cyclotron measurements and maximum energy method in Tokyo Tech. And we could map electron density and indeed demonstrated there is such partial covalency between lanthanum and oxygen. Not only that it was there, but it was more than it was expected. So the experiment showed that our theory was conservative. It was lacking between strontium and oxygen, so we could see that lanthanum is quite interesting, and most of the A sites behave pretty boring in a pretty boring way. Then we move further. Those solid oxide fuel cells operate not only in oxygen atmosphere, they operate in air. And air has at least two other important components, which would be CO2 and water. The reason we did those simulations was because there were two different groups performing experiments with those electrodes, which were exactly the same electrodes produced here in Japan, but one of the measurements was performed in Japan, the other measurement was performed at New Mexico, and they were getting very different results for the oxygen exchange on the surfaces. The one in Japan was working really very well, while the one in New Mexico was showing very poor oxygen exchange with atmospheric oxygen. Now, at that point, we knew that there is no mistake in the experiments being performed, so we realized that there should be something different in the atmosphere. And we looked what is the difference between the atmosphere between Japan and New Mexico. And well, Japanese summer is very humid. So air in Japan is mostly water in the summer, while the New Mexico weather is very dry, so there is no water. CO2, however, is constant around the world. So what we looked at was CO2 competition against water competition for absorption on the surface. And we saw that both molecules will interact with those surfaces without any activating barrier and form either surface hydroxide or surface carbonate. What we, however, seen is that surface carbonate will completely block the oxygen exchange reaction, while hydroxide, surface hydroxide will actually enhance it and will have no negative effect on it. Another thing we've seen is that if water is pre-absorbed on the surface, or if for some reason we have high humidity and water is there before the CO2, water will actually create a protective layer on the surface and significantly delay or even stop the carbonate formation. Performed the experiment to prove it in dry CO2. We saw immediately the carbon peak appearing on the surfaces of strontium titanate. On wet CO2, there were no carbonate peaks, and we could reproduce the activation barrier by temperature dependency, seeing what would be the temperature which will lead to the carbonate peak, carbonate formation. Performing frequency analysis, we could actually understand that we do not have a thick carbonate layer, but what we have on the surface on the material is a single monolayer by just figuring out that what they experimentally see would be the parallel vibration to the surface, which does not exist in the material itself, but only in the monolayer. So it is a single monolayer carbonate formation blocking the surface activity of the material. We developed a mathematical model based on Langmuir absorption theory, which takes into account competitive co-absorption between CO2 and water, and also competitive evaporation between CO2 and water. I won't pass you through those equations, but we can discuss later if you're interested. The results would show that at low temperature, the surfaces are mainly hydroxide. And as you increase the temperature, the hydroxide will be slowly evacuated and replaced by carbonate. And at operating temperature, only a small amount of the surface would be hydroxide and oxide, and most of the surface would be carbonate, so the active sites will be rather limited. If we have dry conditions, the carbonate will be formed at much lower temperatures, reach to almost 100%, and block the active sites on the surface. And if we have humid conditions, our model showed that even to elevated temperatures, we'll have surfaces mainly of being oxide and hydroxide. Carbonate formation will be delayed, and most of the surface will be catalytically active for oxygen reduction reaction. Hence, understanding the gas mixture interaction with those materials is quite important, not only catalytic activity for the target molecules we would have there. Looking at the importance of lanthanum as an element which has this residual electron density for catalytic activity on the surface, we wanted to see if lanthanum is actually also important for the oxide ion transport in those materials. They wouldn't work if they do not transport oxygen, and one of the key things is make those materials better conductive for oxide diffusion. So we looked at LHGM, lanthanum, strontium, gallium, magnesium perovskite, which is standard in experiment for electrolyte in solid oxide flow cells. And the first thing we looked at is oxygen diffusion on a lanthanum H, lanthanum strontium H, and strontium H. Our activation barriers for those calculations showed that oxygen will diffuse preferably at lanthanum H, higher activation barrier on lanthanum strontium, and strontium. Now that would be in line with the idea of spherical hydrons. Lanthanum would be slightly smaller than strontium. So one would imagine that the reason would be a spherical hydrons. However, our explanation would be that in the transition state, those partial bonds between lanthanum and oxygen, which are formed, will lower the activation barrier and make it easier for oxygen to propagate. Then we moved further for A-site mobility within those materials, or lanthanum mobility within those materials. We calculated the jump of lanthanum into the neighboring site and jump of strontium into the neighboring site. Now, lanthanum would be smaller, so we would expect that lanthanum, if we look just at spherical hydrons, lanthanum will have lower activation barriers. Strontium should have, lanthanum will have lower activation barriers. Strontium will have higher activation barrier. However, both experimentally, we know that we have strontium segregation and big strontium mobility towards the surface, and and also theoretically, we could see a higher activation barrier for lanthanum, which is just counterintuitive to their size dependence. Indeed, the reason is that as both lanthanum and strontium will have a charge of +2, not +3 strontium, so the residual electron density on lanthanum, not +3 lanthanum, the residual electron density of lanthanum will be there to bind partially covalently with oxygens in the lattice. We will have to move with the same charge with the Coulombic interaction to the neighboring site. But in order to move lanthanum, we will also have to break the bonds with the oxygens in the lattice, those partial covalent bonds. And this would be the additional penalty, energetic penalty for mobility of lanthanum. It was even more interesting when we looked at B-site mobilities. Now, a B-site should jump between two neighboring sites, passing next to a lattice oxygen. This will require a curved pathway, and it would be quite intuitive to think that if we remove that lattice oxygen in the middle, we have a vacancy in the middle, we will have first lower activation barrier, no spherical hydrons, and second, we are going to have a straight pathway between both sides. However, even with a vacancy, we have a curved pathway, and once we have a vacancy, the activation barrier increases, not decreases. Now, again, the reason for that we found is that in the transition state, the transitioning B-site, which is a highly charged transition metal, will prefer to have as many bonds to oxygens around, which will reduce its charge and energy during the transition, instead of having bigger space to transit through the material. Once again, the bonding interactions were much more important than spherical hydrons to transport through those materials. Now, just ignore the time. Okay. Then I was many times asked at conferences, mainly by Professor Harry Turer from MIT. Well, it's very interesting about lanthanum, but let's go the entire table of rare earth elements. And how about praseodymium? We do know that praseodymium is much more active than lanthanum. So at that time, we started looking at both praseodymium nickelate, lanthanum nickelate, quite similar materials. And what we could see is that the both materials have very different electronic distribution close to the Fermi level. In the case of the lanthanum nickelate, we have the nickel oxide layers outside and lanthanum nickel oxide electrons close to the Fermi level, and lanthanum electrons much deeper within the material. So we need much higher over potential in order to use these electrons. However, in the case of the praseodymium oxide, we have praseodymium just at the Fermi level, so it is itself a catalytically active species. Then all those materials can accommodate additional oxygen within the lattices. So we wanted to know what happens when this additional interstitial oxygen is occupied in the lattices, mainly because we know that we cannot get very high occupation there, so it's being stopped. And in the case of praseodymium nickelate, the holes would appear at the praseodymium, while in the case of lanthanum nickelate, they will be within the nickel oxide layer. So we will be having a very different hole distribution. Beside the hole distribution, we looked at activation barriers, and that would be the activation barrier on praseodymium nickelate without any interstitial oxygen. So we would have activation barrier for oxygen dissociation of about 1 electron volt. Now, if I have interstitial oxygen occupation, the activation barrier will be similar, but the reaction will be strongly endothermic. So once we have oxygen dissociated on the surface, propagating and filling the interstitial layer, that oxygen will make the further oxygen dissociation endothermic, and as a result, will kill the catalytic activity of the material. Or it's a self-cannibalizing reaction. At first, we have the material catalytically active, but once the material is being oxidized, it will stop the further dissociation of oxygen and will block the catalytic activity. So it's very important to drive away those oxygens from the interstitial layer. We looked also at other electrolytes with fluoride structure, which would be yttrium stabilized zirconia, ceria, and bismuth oxide, with bismuth oxide being one of the most interesting species. We were challenged to explain the difference between delta bismuth oxide and alpha bismuth oxide. Now, delta bismuth oxide would be the best known solid oxide oxygen conductor, while alpha bismuth oxide, exactly the same material with a different lattice, will be one of the worst. And this phase transition was yet to be understood. So what we looked at is that bismuth is not really the typical metal oxide as everything else. Bismuth is actually a post-transition metal element, much more similar to phosphorus and to nitrogen. It has lone pair, and this lone pair, unlike the other transition metals, has strongly localized electrons. Now, the crystal lattice can organize these lone pairs in such a way that they will open pathways for oxygen transition, or they will face each other and block the pathways for the oxygen transition. So here was very important to understand that the different crystal structures will allow or forbid oxygen diffusion in the material by strongly localized electrons of the lone pairs. Very quickly, at the moment, we are performing simulations, automatized simulations on oxygen diffusion in many perovskites. What we do is we are systematically changing A site, B site, dopant site in the perovskites, and we are doing systematic VFT calculations in order to get understanding on what controls the oxygen diffusion in those materials. A lot of data has been obtained. We can see that some materials have very similar oxygen diffusion, and it's independent by the doping. For other, we have huge differences dependent on the doping. We found that octahedral distortion is the one criterion which matches closest the differences in the oxide diffusions. So we could see that octahedral angles at the B sides, when those octahedral angles are significant, we have very good oxide diffusion. And when those octahedral angles are close to 180 degrees, we have quite poor oxide diffusion. We continue this data science approach in order to understand better what controls the oxide diffusion within those materials. And very quickly, I would like to move to the conclusions. On perovskite surfaces, aeosite terminations, with aeosite terminations, oxide vacancies are the key factor for catalytic activity. However, the mechanism is very different between the first and second group A sites and rare earth elements A sites. In that case, we have residual electron density, which is important for the oxygen dissociation. Praseodymium is rather special and has much better catalytic activity compared to lanthanum, mainly because of its electron distribution. And lone pairs and bismuth oxide is what controls the differences in the oxide diffusion in the different lattice phases. We need a better classification of perovskites based on different electronic properties and also octahedral distortion in order to understand and design better materials with better oxide transporting properties. With this, I would like to thank all my collaborators over the years, members of my laboratory in the past, and thank you very much for your attention.
Thank you very much, Steve Saksay. So, we talk about questions and comments. Yes.
Thank you very much for interesting talk. And I'd like to ask one question regarding the transition metal moving, despite that there is no satellite vacancy. So transition metal try to get some bonds near to the other cation. So in this case, not directly goes to the center of the oxide vacancy.
No, not to other cations, to the other oxygens. The transition metals needs at the transition state needs maximum oxygen population. So moving charge costs a lot of energy. Transition metals are usually highly charged. The moment you take the transition metal outside of its place in the lattice, you're breaking the bonds which are compensating each charge. You're removing the contra ions, and now you're moving higher charge. As the charge is maximized, you have maximization of the activation barrier to jump to the other side. However, if at the transition state in the middle, at the saddle point, you have a lot of oxygens around, a big oxygen population. This oxygen population will act as a coordination sphere, and this coordination sphere will minimize the charge on the transition metal, hence minimizing the activation barrier and stabilizing the jump on the metal.
Despite that, I mean, the path becomes longer, but
the path is longer. Yeah, there's a thing like because it's more or less like really less than half a nanometer jump. So the path length doesn't really matter that much. It really matters what is the surrounding, what is the coordination sphere around it. So it's not the distance, it's not the spherical hindrance, it's how many bonds are around to give hand and reduce its charge in the middle.
Just let me know how much activation barrier reduced between the
with the
without oxygen vacancy.
well, I don't really.
Just let me.
Yeah, here it is. So without and with oxygen vacancy, it's 1 electron volt difference.
20%.
Yes, it's 20%. Well, it's more or less 1 volt, 20%. That's about 25% would be 1 volt.
Thank
You any other questions? Comments? No, let's thank Staykov again. And the final speaker of this session is Professor Chandra Veer Singh of University of Toronto. And please.